Hello, everyone. My name is Andre. I'm a marketing manager here at Unchained Labs, and I will be your moderator for today's seminar. We will have a Q&A session at the conclusion of the presentation. All you need to do to submit a question is click the Q&A button in the Zoom bar at the top or bottom of your screen, depending on your settings. We will, of course, try to get through all your questions at the end of the presentations, but we would also ask you to not submit your question anonymously so we can follow up in case a longer discussion is needed. But again, we will try to get through as many questions as we can at the end of the presentation. Now, it is my pleasure to introduce you to Kevin Lance, today's presenter. He's product manager for Stunner here at Unchained Labs. He will take us through Stunner's unique ability to characterize ADCs at high throughputs, opening a door to optimizing your reactions, your conjugation reactions with low time and volume requirements. And now I'll hand the floor over to Kevin. Kevin, how are you doing?
I'm doing well. I'm excited to talk about ADCs, really popular topic these days.
All right, it's all yours.
All right, let's get into it. Okay, so welcome to Lose the Lag with high throughput and flexible ADC analysis on Stunner. I first want to explain, what I mean by lose the lag. So when you're trying to uncover the secrets of your ADCs, you're usually about to enter a new frontier filled with unknowns. So there's going to be a lag between encountering the unknown and discovering what's waiting for you inside of it. Is it a pitfall like aggregation that they could be around every corner? Or is it even something simpler like even quantifying by UV vis, where that process and that assay usually starts out as a mystery? So the first unknown to uncover and demystify is the age-old question of how much. If you have a sample, what's the quantity, concentration, how much do you have? For a simple antibody, that's a pretty straightforward measurement. But when it's an ADC, we're now exploring the unknown and asking how much of the antibody we have, how many molecules of the drug we have per antibody, and how good a shape is that antibody still in. And then, of course, the ratio, drug-antibody ratio, DAR, between the antibody and the drug that's conjugated itself. So for answers to all of these questions for ADCs, we can turn to the Stunner. And at the same time as answering all those quantification questions, we can tell if aggregation is starting to be a problem. So when you start evaluating techniques to answer questions about quantification and about aggregation, different techniques are useful for different things. So if you want to evaluate the question of how much do I have, what's my DAR, and you turn to UV vis, that's an excellent tool for protein quant. But if you want to answer questions about what do I have any aggregates, you can turn to a different technique for dynamic light scattering to understand size and aggregation. So Stunner is about bringing those two technologies together so you don't leave any questions about your ADCs unanswered. How Stunner works is to take a 2 microliter sample and you load it into a Stunner plate where it's a normal 8x12 96 well plate that's actually had each one of its wells replaced with a microfluidic circuit. So you can see that microfluidic circuit illustrated here. When you pipette in 2 microliters into the circuit, Stunner takes it from there and can do a read of UV vis to understand how much you have, in your case of your ADC, how much protein and how much drug is present, and do a read of dynamic light scattering that's perfect for proteins and understand if you have the right size or if any aggregates have started to become a problem in your sample. If you're dealing with the full plate, you can get 96 concentration measurements in about 10 minutes. And if you want to get 96 concentration and size measurements, that'll take about an hour. For even heavier workflows, because this is a plate-based method, it's also something that's very friendly and compatible with automation. So what this looks like is, kind of zooming into the microfluidic wells, we can see exactly what those sample microfluidic wells look like with the help of some fluorescein and a black light. So in 2 wells, we've already added 2 microliters of fluorescein. But as you can see, to load another sample, you simply add in 2 microliters into a well, and that sample wicks into the sample plate. And that's done in real time, so that sample pretty quickly is secured inside of that plate. From there, you put the Stunner plate into the instrument, and you start getting answers. So here I'm going to start by showing some sizing data that's done from the dynamic light scattering of the DLS of the instrument. So in this case, we have some example proteins. Just start with some standards that are off the shelf. So here we have thyroglobulin and ovalbumin, and each of these are done in triplicate. So this is 6 total wells. But you can see that the dynamic light scattering in all of these cases is precise enough that the replicates overlay right on top of each other. On the left, we're looking at the intensity distribution, which is going to tell you where the intensity of light is strongest coming from your proteins. And usually people are interested in speaking about, mass distributions in the world of proteins, because we usually think about things in terms of milligrams per milliliter instead of concentration. So on the right side of the slide in blue, you can see how the size of these proteins is related to the concentration. So in other words, we have a ovalbumin that's smaller than a thyroglobulin, but they're about the same concentration in your sample. This helps us understand specifically when we're looking at aggregates, how big of a problem there is with aggregation in our sample. So if we look at an example of that, we can actually spot aggregates ASAP with this dynamic light scattering technique. So here we have two samples. One is a completely happy antibody without any aggregates, and the other one is where we've taken the antibody sample and spiked in a small population of aggregates. On the left, with our purely happy antibody sample, we have a nice monodisperse intensity distribution as well as a mass distribution, where again we have an overlay of 6 different replicates, and they're showing incredible precision. In our sample where we've spiked in aggregates, now we have signal that's appearing in the intensity distribution to show that there are some aggregates present in our sample, which is great because these are actually really, really rare aggregates, but dynamic light scattering excels at seeing aggregates even if they're rare. So they'll pop up very strongly on the intensity distribution, and by mass, it shows how big of a problem we have, which is to say we know it's a 1% spike in aggregate solution, and there's about 1% of this signal right there in the mass distribution. So that's how I would typically use dynamic light scattering to understand average size distribution, and if aggregation is starting to become a problem in our sample. All right, so now let's start talking transition from the world of antibodies to the world of ADCs. So we'll start with an example where we've conjugated an antibody to an Alexa fluor 350 NHS ester small molecule as a model. So in this case, if we're going to start by quantifying these, these ADC models, the one way to do this on Stunner is by first measuring each component part. So the absorbance of a protein, that's pretty standard. If you're measuring just an antibody, this is the step you can skip. But for ADCs, it's helpful to take a dilution series of your antibody. And Stunner will then learn from this dilution series what the spectra of that antibody is. At this, in a separate experiment, you can take an Alexa fluor 350 NHS ester, our model drug or small molecule, and also run a dilution series on Stunner. In this case, where Stunner really shines, it's the ability to learn the absorbance spectra of that Alexa fluor 350 molecule, and then it's going to save that as an analyte in its software. Now, where that starts to become really, really useful is this next step, where you can take the total absorbance that's done from a UV visit experiment, shown in black, and Stunner now knows the underlying absorbance behavior of the antibody and of the drug and linker component. So it can break down that total black signal into its component parts. It will unmix them into green, which in this case is the antibody, and blue, which is the drug and linker. And since we can unmix that total signal into its component part, we can then quantify, get to how much antibody we have, get to how much drug we have, and importantly, DAR. This is the kind of thing that you can do with any sort of conjugate. So on the left, we're again showing an example of an antibody-drug conjugate model where we've quantified the antibody and the drug concentration and expressed the DAR. This is something that Stunner will automatically calculate for you all the way from absorbance to concentration and DAR. And on the right, we're showing actually an antibody-oligo conjugate where we're looking at both an antibody and an oligo separately and quantifying those nucleic acids and antibodies separately to get a ratio as well. Okay, so that's the quantification part and kind of at a high level how that works. If we want to start exploring that conjugation of our antibody and Alexa fluor 350 NHS ester a little bit closer, we can take a look at 3 different conjugation ratios where we're starting with our standard antibody and looking at conjugation ratios of 20:1, where we have 20 parts of drug to antibody, and 40:1. And by looking at our size distributions, we can see that as we start to conjugate more drug to this antibody, we'll see a change in size. This could be just because the molecule is getting larger, or it could be because we're more likely to have small amounts of aggregation present when we start adding drug molecules to our antibody. But either way, we can understand the change in size and size distribution as we increase the reaction ratio of our conjugation reaction. If we're going to then take our DAR and our quantification reaction, we get pretty much exactly what you would expect. Whereas your reaction ratio goes up, your DAR also increases, but importantly, we're able to quantify recovery at the same time because we're understanding our antibody concentration very quickly and simply across all these different reaction ratios. And like you might expect if you've done a lot of conjugations, as you start to get to really extreme reaction ratios, yes, your DAR is higher, but your recovery is dropping as that reaction is more intense on your antibody. We can also see that as we get to those higher conjugation reactions and higher DARs, it does also hurt stability of our antibody, since we start to see an increase in hydrodynamic diameter, that's the top of the blue bars, and we see an increase in polydispersity index, which is our gray dots. So as polydispersity index goes up, we know our sample has more and more aggregation, is becoming more polydispersed. So all of that's gathered in a single read on every single sample that you run on Stunner. Okay, so next let's take that type of experiment and we'll expand it a little bit. So now we're going to take an antibody and conjugate it to fluorescein isothiocyanate, that same Alexa-4 350, but this time with the malamide linker, and then that same Alexa-4 350 with an NHS ester again we saw before. If we start to compare those different drugs and those different reaction conditions that we want to try to optimize, what we're seeing is at different reaction conditions, different molar ratios, we get higher DARs, like we saw before. This varies a lot across those three different dye molecules, and then we also get varying amounts of recovery across the three different dye molecules. So in a single read on Stunner, you can start to evaluate which drug you might want to optimize for, which reaction ratio you might want to optimize for, and how your recovery process is going in terms of efficiency. Beyond just quantification, we also get that sizing information. So here we can see the z-average size is the top of the blue bars, and the PDI again is the gray dots. And where we saw lower recovery percentages by quantification, DLS kind of tells a similar story, where that FITC at a high reaction ratio, which had the worst recovery percentage, also has the highest size and a problem with aggregation as indicated by the PDI increasing. So another thing we can do with that DLS, aside from just screening and evaluating different conditions and techniques, is use it as part of a stability study. So in this case, DLS is going to be incredibly sensitive to look for aggregation. So if we check out in this case, a 21 mole ratio of our NHS ester compound, which had the second highest DAR, we can see that at day one, it's very nice and monodispersed and the correct size that we'd expect for an ADC. But after 7 days of fridge storage, we start to see a small but detectable amount of aggregation. So we see these very large aggregates present in the intensity distribution, even though, once again, our mass distribution shows how big of a problem this is quite a rare amount of concentration, which kind of indicates that DLS is the right technique for this because it's going to see those rare small aggregates, but something like SEC might miss those large and rare aggregates. So this helps us understand which conjugation conditions, which buffer conditions, where stability might start to be impacted. Okay, and with all of that information, we can then start to screen and select only the best drug molecules that we want to move forward with, only the best molar ratios for our reaction, and understand what the DAR size, PDI, and recovery percentage is for our process. Okay, so that's all a great example of using an antibody in a drug condition where we can quantify the drug separately, but sometimes you can't even get your hands on your drug to read it by UV-Vis. In this case, we might have an antibody where we can run that dilution series and teach Stunner its spectrum, but our drug might be too toxic, too insoluble, or maybe it even changes its absorbance after conjugation. So it's not going to follow that same kind of logical flow that we had before, but we can teach Stunner its spectrum from a dilution series. So for this particular case, what we're using is what I call a double standard, where we have an antibody standard, and that's actually been conjugated into an ADC mimic standard from Sigma. So we will use this SIGMAB antibody at the same time as using its universal antibody standard in this next experiment. So in this case, we actually don't have the free drug available to us. So what we're going to do to set up this experiment is run a kind of simulated dilution series where our antibody concentration stays the same. On the left, we have pure ADC, and on the right, we have pure antibody standard. And we'll just mix them so that what ends up happening is the drug actually gets, diluted as we go forward with it, but the antibody concentration stays the same. So this way, we're actually going to teach Stunner what the spectrum of that conjugated drug is, and it will ignore the spectrum of the antibody itself. The end result of that kind of experiment is that we can take the total absorbance of our ADC and again unmix it so that it's looking at the antibody concentration, the antibody absorbance shown in blue, and actually that drug and linker concentration shown in green. And once again, we can quantify, get to mg per mil, and get to DAR the same path as we did before. So that's how Stunner makes for an all-in-one biophysical readout of ADCs, getting you concentration, DAR, size, and aggregation in just moments. If you want to read more about this experiment, looking at different conjugation techniques, different drug candidates, or just how we processed all of our samples, you can look at the app note Conjugate, Cleanup, and Characterize ADCs under Unagi and Stunner. Stunner was used for quantification and sizing of all of our conditions, and then Unagi was used for cleanup of all of our reaction conditions, filtering out free drug, and really exchanging into different buffers as well. So that's a great example of how to use Unagi in the field of ADCs. And actually, those are just two of our parts of our ADC Dream Team, where Stunner and Unagi take care of what I talked about today, and then Uncle can really help you explore more on the stability side of things, where we have additional app notes and information on that. So that's the right tools for ADCs and how they can help you go faster, handle all those problems we have to outrun, and really explore the unknown when it comes to working with your ADCs. And with that, I'll pause here and see what questions are out there for me.
All right. Thank you very much, Kevin. And I'm very glad to see that you also shaved for us and you're not like walking around with your hat and your whip and everything. Thanks for a great presentation. Thanks for taking us through how to use Stunner to characterize ADCs and for their drug-antibody ratios, and how to watch out for aggregation at the very same time so that you can smoothly optimize all of your conjugation reactions. We have some great questions on the list already. You in the audience, if you have anything that's burning under your nails, type it into the Q&A bar at the top or bottom of your screen, and we will tackle that. Okay, let's get through it. How long does a Stunner analysis take, Kevin?
So there's a few different options for how much data you want to gather. If you're looking at just the UV-Vis concentration or DAR information, that you can read an entire plate in about 10 minutes. If you want to get sizing information as well, DLS takes about 20 or 30 seconds per sample. So that'll take about an hour for the whole plate to be read.
Okay, very good. So still all very manageable if you compare it to some other techniques. Can Stunner be used in a GMP environment?
Yes, so Stunner has 21 CFR Part 11 software tools that are available. It makes it very easy to port that into regulated environments. We also have IQ/OQ and standards available to make sure that you have everything you need in those regulated environments.
Very cool. User asks, does Stunner give directly a concentration or an absorbance value?
It does both. So if you just want to get the absorbance value, the OD measurement, that's where all of these UV-Vis experiments start. And then we've put a lot of time and effort and thought into designing Stunner software so that it gives you the answer that you want. You don't need to take that OD and run to an Excel with it. So you set up analytes in Stunner software to calculate from OD all the way to the concentrations, or in some cases DAR, that you actually desire. So there's a few ways of setting that up, but we've made it as easy as possible.
Awesome. Thank you for answering that one. Not quite sure what is referred to here. Would this work for proteins that aren't monoclonal antibodies? So I guess the applicability of Stunner as a technique to characterize any protein, not just ADCs or monoclonal antibodies.
Yes, yeah, absolutely. So we've had groups that look at this with Fabs, with peptides, anything that absorbs will work on Stunner, and then you can follow the same kind of logical flow. So I've seen some groups that are doing, instead of antibody oligo conjugates, doing Fab oligo conjugates, those kinds of things are no problem.
Awesome. Is the extinction coefficient of the free drug needed for ADC analysis?
So if you know the extinction coefficient, you can just type that in manually. The other, and then Stunner will use, the wavelength and extinction coefficient that you want. You can still teach Stunner the spectrum, and it will do all the fitting and do all the math for you. The other approach is if you start with a stock concentration where you know the concentration. So let's say I'm weighing out my drug, I have a few milligrams per mil, and I dilute that out, then I know my stock concentration. Then Stunner can calculate an extinction coefficient for you because it has a known concentration, it's measuring OD, and you're doing a dilution series to make sure that you're being accurate. That's something that can be done with the standard experiment on Stunner.
Awesome. So basically, several options to get to this. Are blanks compulsory to get UV-Vis data?
No, you don't need blanks. I like blanks, but yeah, there's a few options here. You can go with no blank. You can go with stored blank, where you've maybe run your buffer on a previous day, and you can store it into the spectrum. So those are two options where if you don't want to run a blank on the plate, you can do those.
Okay, very good. Does Stunner account for the presence of free drug in a sample when providing the DAR output?
So Stunner's not able to look at free versus bound drugs, so you do need to clean that up ahead of time with some kind of filtration. In our case, we actually used Unagi for that. So there's some experiments in that application note that I referenced proving that we did clean up the free drug through our filtration using Unagi.
Right, and that kind of ties in with the other question that is here. You mentioned Unagi towards the end. How does that work to clean up samples? So as an automated ultrafiltration, diafiltration step that will, based on the membranes that you use, be able to remove small molecules like unreacted drugs. So I guess you just hit two answers in one. I see is one more question here. Will Stunner applications be able to qualify as per ICH Q2R2 guidelines? Have you heard of that?
I'm not extremely familiar with that. That's something I'll have to follow up with that particular user later.
Yeah, it was not anonymous, so we can follow up with this user. Very good. Yeah, that brings us to the end of our Q&A, unless going. Okay, no more. Thank you very much for answering all these questions, Kevin, and thanks again for a great presentation. I want to thank everybody in the audience for joining us today. And if you have any other questions for us, please do not be shy and reach out to us, or you can reach us at info@unchainedlabs.com or through our website, www.unchainedlabs.com. We always like chatting with you. We would love to connect with you. Thanks a lot for attending our virtual seminar. Have a great rest of your morning, afternoon, night, wherever you are in the world. And thank you. See you around. Thank you.
Bye.